Hey guys, this is the second to last video for the semester. Yay, alright. Everybody cheer, woohoo. Okay. So, what is it over? Well, this will be over 7.3, and here we'll be optimizing functions of two variables. So, remember back to chapter 3 when we started taking derivatives of functions and trying to find relative extrema, relative maximums and minimums, and we had applied optimization problems where, remember the hotel room problem where you had to maximize revenue given a number of rooms and a price, something like that, or area type problems where you were given an area with a perimeter restriction, the amount of fencing, that kind of thing. That was all optimizing functions. Optimizing here means finding a maximum or a minimum. But that was functions of one variable, right? Here we're going to optimize functions of two variables. So it's the same basic idea that we'll have a function, but this time it's of two variables, and we'll be trying to find a maximum or a minimum, a relative maximum or a minimum. And there's a set way for us to do that, just like we had our first or second derivative test back in chapter 3. Here we're going to have something called the d-test. So there it is, relative extrema and the d-test. Okay, so let's remember what relative extrema are. So relative extrema are maximums or minimums compared to the things around them, but what does that look like in the context of a two-variable function? So we say a function of two variables has a relative maximum at AB if, well, that means that f of xy is less than or equal to f of AB, so that means f of AB is the biggest guy for all points that are close enough. So that just means if you look close to AB, then that is sort of a local or relative maximum. Still kind of looks like the top of a hill, that kind of deal, but here we're just talking about, remember the graphs look a little bit different, right? It's not just a curve and it's top of a hill. It's here a three-dimensional picture for that graph, and that relative maximum still just looks like it's the top of a hill from all directions there. Notice I've got it pointed out in this graphic here that for this relative maximum at AB, that means that the partial derivative with respect to x at that point is 0, and the partial derivative with respect to y at that point is 0. Right? So we'll actually be using those to find these guys. And just, we won't use this term a whole lot. We're not going to be, whatever. Anyway, the point is that's a critical value. You guys remember, hopefully, critical values back in chapter 3 when we started doing things like this, setting a derivative equal to 0. Here, if the partial derivatives are both equal to 0, then we still call that a critical value. And this maximum can happen at a critical value. For a minimum, the other side, it's just the exact same thing, but that picture would sort of be upside down, right? So there's your picture of it. And that just means that when you look close to your point, it's the least guy. It's less than everything else, and that would be something like this. And notice again that both partial derivatives would be equal to 0, right? It's still a critical point, but where both partial derivatives are equal to 0. So if we were looking for these maximums and minimums, just like we did before where we found the critical values, we took the derivative, set it equal to 0, we're going to do that again, but this time that requires taking both partial derivatives and setting them equal to 0 at the same time and finding a solution to where both partial derivatives are equal to 0 as opposed to just a single derivative being equal to 0. And they can only show up, like we said, when both partial derivatives are equal to 0. And just like before, just because both partial derivatives would be equal to 0, just because we have a critical value, doesn't mean you have to get a maximum or minimum. And in this case, remember back to our function of one variable case, if you looked at like y equals x cubed, you could have a point sort of at 0, 0 where it was a critical value, but it's not a relative maximum or minimum. So now what does that look like, that sort of scenario for functions of two variables? Well, it looks like this. All right, so this point here would have y partial derivative equal to 0. Right, so if you sort of travel this way, it looks like that derivative would be equal to 0. And x partial derivative equal to 0, if you travel this way, that looks like it's got partial derivative equal to 0. But that thing is not a maximum or a minimum. And we actually named these guys based on what that picture looks like, and that's a saddle point, right? That looks like it's a saddle right there at that point. And so those points where it is a critical value, both partial derivatives are equal to 0, but it is not a maximum or a minimum for that surface, we call that a saddle point. Okay, so here is how we find relative extrema or saddle points for functions of two variables. It's called the d-test. It's basically just the step up, the higher level equivalent to the second derivative test that we used back in chapter 3, right? Remember the second derivative test? It was the thing on our third exam where you had a critical value, you could plug it into the second derivative and figure out the concavity, that kind of thing. So without getting too much into the detail of it, this is basically just a step up of that. This is the evolved version for functions of two variables. And what we'll do here is go through the list of these steps, what this d-test is, and then we'll go through some examples using it. And this d-test is not something that I expect you guys to memorize. I will give this to you on a formula sheet on both our last exam, and you will also get that on the final and on any quizzes that we have or anything like that. You'll get this entire slide right here. Okay, so what is that? So to find relative minimums or maximum values, right? If I say find the relative maximums of this function of two variables, you should immediately think, okay, relative extrema, two variables, d-test. Let's do it. All right, so first step, we need to find our first order partial derivatives, fx and fy, and our second order partial derivatives, fxx, fyy, and fxy. We don't need to find fyx because remember, we're only going to deal with nice functions where that's the same thing as fxy, so we would know they'd be equal. All right, so we find these 5 things. Right, and that's sort of the equivalent of finding our first and second derivatives back in chapter 3. We need to find our first order partial derivatives and our second order partial derivatives. Okay, so we find all these partial derivatives. Now, back in chapter 3, what did we do? Well, we set the first derivative equal to 0 to find our critical values. And that's exactly what we're going to do next here. But the first derivative is not just one thing, it's 2 partial derivatives. So what we're going to do is take both partial derivatives and set them equal to 0. And we need to solve for a solution that's going to be a point, a comma b, an x value and a y value, where both of those equations are equal to 0. That will give us a critical value, or critical point AB, the critical value AB. So that's similar to what we did, but this is the step up. Once you have that critical value, you're going to plug it into, this is where this thing gets its name, is this D function. So you plug it into here, and again, I will give this to you. And what do? Is you plug it into that second partial derivative fxx, which we found in step 1. Multiply that by fyy, where you plug in your point, which we found in step 1. And then you subtract fxy, plug in AB squared, right? So we're going to plug our solution into this guy, and that's step 3. We want to know, just that should pop out a number, what that number is for whatever our solution is. All right, so that's sort of the equivalent to plugging our critical value into that second derivative like we did back with the second derivative test in chapter 3, is plugging it into this D function here. Okay, and then, and I will also give you this entire 4th step here, which tells you what everything means. So you're going to have a maximum if the number that popped out in step 3 is positive, and the second partial for fxx, when you plug in your point, is negative. So if the d function was positive and fxx was negative, then your point is a relative maximum of your function. It'd be a minimum if the d function was still a positive number, but this time fxx was also positive, right? So the d function being positive tells you you do have a maximum or a minimum, and then you look at that second partial for x to tell you which one it is. If it's negative, it's a maximum, and if it's positive, it's a minimum. So that's similar to the concavity. The second derivative, if it's positive, would be concave up, and you would get a minimum, and if it was negative, it would be concave down, and you get a maximum. That's basically what's going on here, where we check that second partial, and the sign of it, positive or negative, tells us maximum or minimum. All right, we get one of those saddle points if that d function spit out a negative number. All right, so if it wasn't positive, if it was negative, then we would say, oh, okay, this point is a saddle point. You don't have to check the second partial fxx. You just know if it's negative, that was a saddle point. And the other option is that that d function spit out 0, in which case the test doesn't work, and we won't be able to determine if your critical value is a relative maximum or saddle point. Okay, so that's the idea of the d-test, right? I'll give you that box, and hopefully you'll have that. If you guys are taking notes and going along, have that off to the side while you're taking your notes, because I'm going to keep referencing it and assuming that you guys can look at it. All right, so make sure you've got that off to the side. If you need to, if you don't have this PowerPoint printed out, pause the video here and you can write that down and keep that off to the side while we go through some examples. And then whenever we have a quiz or exam, like I said, I'll give you this entire slide to work with as well. So if you can just follow these instructions, what we need to be able to do is just find partial derivatives, solve a system, plug things in, and then read off the answer from that step 4. So that's the main idea there. Okay, so let's dive into an example. My instructions here would be find and classify, if possible, all relative extrema and saddle points. So what that means is find all your critical values. That classify means tell me if they're a maximum or minimum if they are a relative extrema, or tell me that they're a saddle point. So what this means is tell me, find all your critical values and tell me if they are maximums or minimums. So this might also say find all relative extrema and saddle points, or find all relative maximums and minimums and saddle points, anything like that, all the same instruction. Okay, and so we know when we see a function of two variables and it says something about relative extrema or saddle points, hey, that's the d-test, let's go to that. So first step of the d-test is to find your partial derivatives fx, fy, fxx, fyy, and fxy. Right, so your first order and the 3 second order partial derivatives we care about. So let's do that. What is fx? All right, so if you guys aren't comfortable with taking partial derivatives, then you should probably go ahead and stop this video and go back and watch the other one first, because I'm going to go through that a little bit quicker than I did in that first video in this one. And without knowing how to do that, you certainly can't do any of the stuff in this section. So it's more important that you would go back and review if you're struggling, and then you can apply this d-test once you're very comfortable taking these partial derivatives. Okay, so assuming you guys are okay with that, what's the partial with respect to x? Well, we get 2x plus y minus 3. What's the partial with respect to y? We get x plus 2y. All right, this is, I wanted to label here, this is our first step. Now we also need the second partials, fxx. And so we go over here to fx and take the partial with respect to x and get a 2. We need fyy, and we look at fy and take the partial with respect to y. We also get a 2. And then fxy, we get 1. And you could double check that by taking fyx, and notice you'd also get 1. But we don't need that. That's just sort of a, if you don't get the same thing, you know you've made a mistake, and if you do it, then maybe you're on the right track. Okay, so we found all of those partial derivatives. Step 2, from that d-test tells us to set fx and fy equal to 0. So that's fx is 2x plus y minus 3, and we want to set that equal to 0. And we also want to set fy, which is x plus 2y, set that equal to 0. And then we want to solve for the point, a point which has an x value and a y value, where both of these are equal to 0. So what that means, in pre-cal you did stuff like this, and we called that solving a system of equations. Right, so I'm hoping you guys, this is not the first time you've seen that. It was covered in the Business pre-cal section, which you should have already taken, but I certainly don't expect you to remember that off the top of your head, but ideally sort of comes back to you. Okay, so there's two ways that we would solve this. We would do something called substitution, where we're going to solve for one of these variables and then substitute it into the other guy to be able to figure things out. We also did something called elimination, where we would multiply one of these equations by a constant and then add our equations where one of the variables would be eliminated. I think for all of our examples, substitution works and is not too bad, so we'll just do that. But if you haven't seen that in a while, then make sure you guys ask about that in class and we can go over it. Okay, so how does that work? Well, our goal is going to be to solve for one of these variables. So to get something like y equals, and we're going to use this fx guy to get that. And then we'll take that and plug it in over here for y. I'm actually going to do this in a different color, just because I can. So if we solve that for y, we'll add 3 over and subtract 2x. So we get y equals 3 minus 2x. So we use that first equation to solve for y. And now what we want to do is plug this thing, what y is equal to, into that second equation, wherever that y is. So when we do that, we get x plus 2, and then instead of a y, we're going to substitute in what we got for y, which was 3 minus 2x, and that is equal to 0. So that's substitution. You use the first guy, or either one, doesn't matter which, but solve for a variable, and then whatever you get, you plug that into the other equation, and you should be able to get a solution for whatever was left over. So here we got rid of the y, and we were left with just x's. So this should now be something we can solve for x. Okay, so solving for x, what do you get? You get x plus, let's distribute that 2, so that's 6 minus 4x equals 0. So that would be 6 minus 3x equals 0. And 6 minus 3x, there it is, equals 0. Add your 3x over, divide by 3, and you'll get x equals 2. So x equals 2, that's the only x value that's a solution to both of these equations being 0. All right, so we need y. So how can we find y? Well, what we're going to do is take this x equals 2 and go back to our thing we had where y equaled something and plug it in for x. Right? So let's plug that in and we'll get y equals 3 minus 2, and then instead of times x, let's plug in x equals 2. So that would be times 2, so that's y equals negative 1. So we only got one solution to this, and it was whenever x is 2 and y was negative 1. Right, so for step 2, setting those partial derivatives, the first ones, fx and fy, equal to 0, we then solved for the solution to those things being equal to 0, that system of equations, as you called it in pre-cal, and the only answer we got one solution, and it was the point 2, negative 1. Okay, so we have our point. We only got one of them, so we only have to test one guy. If you get more than one solution here, well, then you just test both of them and tell me what they both are, or all three of them are, or whatever it might be. So here for the third step, what does our test tell us to do for that d-test? Well, it says plug that point in to that function. So what we want is d of, whoops, not -2, positive 2, comma, -1. So that's x equals 2 and y is -1. And what we're plugging that into is where you guys can hopefully see on there, you plug 2 -1, sorry, into fxx, but fxx is just 2, so it doesn't matter what you plug in, it's always 2. So that's fxx of 2 -1. Now fyy of 2 -1, well, fyy is also always 2, doesn't matter what you plug in, so that's just a 2 there. And then we're going to subtract fxy, plug in the point 2 -1, but fxy is 1 all the time, so it doesn't matter what you plug in, it's still 1. And then we're going to square that. So this is plugging in 2 -1 to fxx times plugging it into fyy, and then subtracting, plugging it into fxy, and then squaring that thing. So what do we get? We get 2 times 2 is 4, minus, well, 1 squared is still 1, so 4 minus 1 is 3. So from step 3, we got that d value of 2 -1 is 3. Okay, now we go to step 4, and we just need to read off the list. So here, we have d of 2 -1 is 3, which is greater than 0. All right, so then that first and second guy, where we talk about max and minimums, that's where d is greater than 0. And it says we need to know what is fxx of 2 -1. But fxx of 2 -1, we found that before. It was just 2, and that's also greater than 0. So when d of 2 -1 is greater than 0, and fxx of 2 -1 is greater than 0, that means what we're looking at is a minimum. So that means the point 2 -1 is a minimum. It's a relative minimum. You can just say minimum here. All right, so same instructions. Let's do another example here where we have a different function of two variables. So there it is. We'll still call it f, but it is different than the last slide. Okay, so since we're trying to find relative extrema and saddle points, and this is a function of 1, 2 variables, we know that we're going to use the d-test. So if this was a quiz or an exam or something, we would definitely go back and bring that d-test instructions right next to our work, which hopefully you guys have, and we're going to follow along with that. So step 1 of the d-test says find fx and fy, the first partials, and then fxx, fyy, and fxy, the second partials. So we're going to do that first. Fx, partial with respect to x. What do we get? So 4xy is 4y, minus x cubed is 3x squared, and 2y squared, no x's in there, goes away. All right, that's the partial with respect to x. Now we need the partial with respect to y. When we do that, what do we get? We get 4x minus 4y. Okay, now let's take fxx. So we're going to go to fx, the first partial, take the partial with respect to x, and we'll get minus 6x. For fyy, we get minus 4. And for fxy, what do we get? We get positive 4. We can double check maybe that we're on the right track. Let's take fyx. Hey, that would also be 4. That's good. So those would be the same. That's what we expect to have happen. Okay, step 2 of the d-test says set fx equal to 0 and fy equal to 0. So that's 4y minus 3x squared equals 0. and fy, which is 4x minus 4y equals 0. 0. There we go. All right, so now we need to find the solution to that system where both of those partial derivatives are equal to 0. So what we'll do is solve for one of the variables like we did before, and then plug that into the whichever equation we didn't use, and we'll be able to go from there. So let's start by solving for y. All right, let's do that. It doesn't matter which one of these you use. We used fx last time just to show you it doesn't matter. This time, let's use fy. Also, I want to use fy because of this squared floating around. I feel like it'll be easier to solve for y over here. So if we do that, we'll get y equals what? Well, we'd have to move the 4y or 4x over and then divide by 4. Well, what does that look like? We'll go ahead and do that off to the side here. If we move the 4y over, we get 4x is 4y. Divide by 4, you get x equals y. Okay, so y equals x is what we get from that. And I'm going to erase that. So if you're not sure where that came from, rewind. Rewind, like that's going to be a thing, like this is a VHS tape. Just click back. This is YouTube after all. Okay, so y equals x. That's what we get from this guy. If we had solved for y, I just want you guys to see this. I'm going to do it in purple over here, but don't write this part down. If you had solved for y using this equation fx, what would you get? So if we added the 3x squared over and then divided by 4, you would get y is 3x squared over 4. And that would absolutely work, but that looks a little bit uglier than just y equals x. So what I'm going to do is, even if you did that one first, say, hey, this is kind of ugly. Maybe it'd be nicer to do it with the other equation. Solve for y with the other equation. But this would absolutely work. Wouldn't be an issue. It's just a little easier if you use the partial with respect to y to solve for that. Okay, so that's what we're going to do, but I just wanted you guys to see that what you would get the other way. And if you want to try it with the purple guy, that's fine. That would absolutely work. You just have to plug that into the one you didn't use there. Okay, but we'll use y equals x. So I'm going to erase all of this. So we've got y equals x, and what we want to do is use this and plug that in for y up here in the equation we did not use yet. Okay, so what we get is 4 times, and then just instead of a y, we plug in x. So that's 4x minus 3x squared equals 0. There we go. And how do we solve that? Well, let's factor out an x, and we get x times 4 minus 3x equals 0. And then what we do with that is that gives us an x equals 0 and a 4 minus 3x equals 0. So x equals 0, well, we're done with that one. 4 minus 3x equals 0. We solve for x and get x is 4/3. 4/3. So our answer is going to be 2 points. One point where x equals 0, and the other point where x equals 4/3. Right, so we're going to have 2 points there, a 0 comma something, and a 4/3 comma something. And we go back to this guy to figure out what y is. Well, y is equal to x. So if x is 0, y is also 0. And if x is 4/3, y is also 4/3. So we got 2 critical values from that second step, 2 solutions to this system where the partial derivatives are equal to 0. And we'll have to check both of them in steps 3 and 4 to get all relative extrema, right? Because we know there's now maybe two of them. They could both be maximums, both be minimums, saddle points, whatever, something along those lines. We need to check them both for that d-test. Okay, I do want to do that, but before I do that, I just want to show you guys, in case you did use the other equation, that you would get the exact same answer. So I'll go back to purple. If you guys are following along with what I did here in blue, you don't need to write this next part down. You can just watch. But let's go back to, if we solve for y, remember we got y equals 3x squared over 4. And that's fine, right? But that's our y. Well, then we'd have to plug that in for this y right here, because that's the equation we didn't use yet. And we did that. If we do that, we will get 4x minus 4 times 3x squared over 4. And that thing is equal to 0. Okay, and now these 4's here cancel. And what are we left with? Well, we have 4x minus 3x squared equals 0. And that's exactly this equation right here. So we would get the same x equals 0 and x equals 4/3 and the same y values. Right, so that will give you the exact same solution. It doesn't matter which one of those equations you solve for y for, or you could even solve for x instead of y if you wanted to. You just want to solve for one of them in one of those equations and then plug it into the other one. Right? So it doesn't matter which way you do that here, whether it's the purple or the blue. Either way, we get these 2 points, 0, 0, and 4/3, 4/3. Okay, I'm going to get rid of this now so that I have room again. All right, we'll go back to red here. So step 3. Step 3 of that d-test is we want to plug our solutions over here, both of these guys, into that d function. So we need d of 0, 0. And then we'll also find d of 4/3, 4/3. So what is d of 0, 0? So we need fxx of 0, 0. So we look at this guy, plug in x and y equal to 0. So minus 6 times 0 is 0. And we multiply by fyy of 0, 0. Well, that's negative 4. Doesn't matter what you plug in. That's a constant. And then we subtract fxy, plug in 0, 0. That's 4. And square that 4. So what is that? Well, that's 0 minus 16. So that's negative 16. So there is the d value for 0, 0. We also need the d value for 4/3, 4/3. So again, go to fxx, which is minus 6 times x. So that would be minus 6 times 4/3. That's fxx. Plug in 4/3 for x. And then fyy, well, that's negative 4 all the time. And fxy is 4 all the time. So there is that. Well, what is that equal to? Well, negative 6 times 4/3 is negative 8. So that's negative 8 times negative 4 minus 16. Negative 8 times negative 4 is 32. Positive, right? These negatives cancel each other. So that's 32 minus 16. And 32 minus 16 is 16. So we got negative 16 for 0, 0 and positive 16 for 4/3, 4/3. So now in this fourth step, we need to check both of these guys again. So what happened with 0, 0? D of 0, 0 is negative 16. Whoops, missed my negative sign. And negative 16 is negative. So following that d-test, since we got a negative number, this critical value 0, 0 is a saddle point. All right, so that d being negative means we got a saddle point. All right, now we need to check 4/3, 4/3. So what did we get for that? Well, we got positive 16. Okay, so since that's 16 and that's greater than 0, there's 16, there we go. 16 is positive, so that's that first or second guy from step 4. So we also need fxx, right? So d being positive tells us it is a maximum or a minimum. We go to fxx to determine which. So fxx of 4/3. One more example, same instructions. Function looks a little bit different this time. We have e to the x squared plus y squared plus 1. Okay, so all relative extrema and saddle points, function of two variables. So we should immediately think, okay, we're going to use the d-test. So let's go to that d-test. Step 1. All right, find all of 5 of those partial derivatives that you should see when you look at that d-test. So we need fx, the partial with respect to x. What do we get? All right, well, we're going to get e to the x squared plus y squared plus 1, and then multiply with the chain rule by what? Well, the partial with respect to x of that thing looks like a 2x is going to come out of there. So I'm going to write that out in the front, and that's why I didn't write the e stuff down first. So we get 2x times e to the x squared plus y squared plus 1. For fy, all right, again, we're going to have to use the chain rule because there's a y up in that exponent. And this time what's going to come down is a 2y times e to the x squared plus y squared plus 1. So those are our partial derivatives with respect to x and with respect to y. Now we need the second partials, fxx. And to find fxx, we're going to have to use a product rule, right? We've got a 2x out in the front and an e to the x stuff up in the exponent. So that's going to be a product rule. So the first, 2x, times the derivative of the second. Well, that's exactly what we already found. That was 2x e to the x squared plus y squared plus 1. We already did that. So first times the derivative of the second plus, and we're going to have the second times the derivative of the first, and the derivative of 2x, partial with respect to x, is just 2. So we get 2 e to the x squared plus y squared plus 1. So there is fxx. If you want to, you can combine this 2x times 2x. That would be 4x squared out in front of that thing. You guys can write that like that if you'd wish. All right, fyy. Notice we're going to have to do product rule again here. This time the 2y is out in the front. So the first is 2y. The derivative of the second, well, that's again what we have. 2y e to the x squared plus y squared plus 1. And then we add the second times the derivative of the first, and the partial of 2y with respect to y is just 2. So that looks similar to what we had before. So there is our second partial with respect to y, fyy. Now we need the mixed partial, fxy. Right, so this time we're looking at fx, which is 2x e to the x squared plus y squared plus 1, taking the partial with respect to y. So this time that 2x out in the front is just a constant, so it's just coming along for the ride. We don't have to do product rule. Right, so that comes along for the ride, and now we need the derivative of e to the x squared plus y squared plus 1, partial with respect to y. Well, that's what we already have, that fy guy, and so that was 2y e to the x squared plus y squared plus 1. Okay, and again, you could rewrite this as 4xy out in front. All right, there are all of our partial derivatives. There they are. That's the end of step 1. Step 2, we want to set fx and fy equal to 0. So if fx, that's 2x e to the x squared plus y squared plus 1. We want that to be 0. We also want fy, which is 2y e to the x squared plus y squared plus 1. We want that to be 0. Okay, so this looks a little bit different. It would be difficult here to solve for y and plug it into the other guy. It's going to be harder to isolate y all by itself because of the thing up in the exponent. So what we're going to do here is we need to recognize what we have. And what we have is two things that are being multiplied and set equal to 0. So that's just like if we had something like x plus 1 times x minus 2 equals 0, how did we solve that guy? Well, we set each one equal to 0 by themselves. Remember something like that, hopefully? And we're going to do the same thing here, where the two things that are being multiplied are 2x and e to the x squared plus y squared plus 1. So this is that same train of thought. So let's do that. Let me get rid of this. So what that is we're taking the factors 2x times e to the x squared plus y squared plus 1 and setting them equal to 0 individually. So that gives us 2x equals 0. And if 2x equals 0, that means x equals 0. This guy gives us e to the x squared plus y squared plus 1 equals 0. And the question is, can you ever raise e to a power and have it be equal to 0? Well, remember the graph of e to the x looks something like this, and it never hits that 0. What that means is that you can't have e to the something equal 0. That can't ever happen. It doesn't matter if that something is x squared plus y squared plus 1. Even if it's something like that, it cannot ever hit 0. So that means that this guy gives you no solutions. There's no solution to that. Another way to think about that would be to try to solve for that by taking the natural log of both sides. If you took the natural log of the left, you'd get x squared plus y squared plus 1. The e would go away. But if you took the natural log of the right, you can't take the natural log of 0. That's not defined. And so that would again pop up to be, oh, okay, this does not have a solution. All right, so that means that the only thing we get from fx is that x needs to be equal to 0. Now let's look at this fy guy. We have a similar story. We have 2y times e to the stuff x squared plus y squared plus 1 equals 0. So we're going to set both of them equal to 0 separately, just like we did for fx. So if 2y is 0, that means y is 0. And this guy gives us e to the x squared plus y squared plus 1 equals 0. But that's exactly what we had before that had no solutions. So for the exact same reasons, it's the same equation, still has no solutions. So that means the only thing we got was x equals 0 and y equals 0. So our only critical value is the point 0, 0. Okay, so that's the end of step 2. We found the critical value, only one of them, and it was 0, 0. This kind of looks like a little dude, maybe. Like, if he was smiling. Yeah, nice. Okay, step 3, we want to plug this point 0, 0, our solution, into that d function. So we go to fxx and plug in 0, 0. And we're going to go to fyy and plug in 0, 0. And we also need to plug 0, 0 into fxy. So I will let you guys try that on your own, and I'm also going to show it to you. But to do that, I need to erase my green and blue stuff over here. So if you don't have the rest of this stuff written down, copy down, pause the video, and copy that down now. I'm about to erase it. Okay, here I go. I'm going to keep the drawing of my little dude. Try to, if we have room. All right, now we've got some room. So what we need is f(x(x) of 0, 0. Okay, so what is that? Well, that's 2. We're looking at let's switch to blue here. We're looking at this guy. So that's 2 times 0. That's 2x. So 2 times 0 times, well, 2 times 0, e to the whatever. But that's just going to be 0. This x is going to kill off everything else. So would this one. Because it's all being multiplied, it's just a bunch of stuff times 0. So that means that what we really get is just 0 for that first part, plus, then we've got 2e to the x squared plus y squared plus 1. So that's 2e to the, well, x is 0, so x squared is 0. So that's going to go away. Y is 0, so y squared is 0. That's going to go away. And we're just left with 2e to the 1. So that's 2e. So that's f(x(x) of 0, 0. All right, how about fyy of 0, 0? Well, that's going to be very similar. For fyy of 0, 0, we're going to this equation here, and we're plugging in x and y equal to 0. But this y or this y, both of them, are going to make that whole term, just like the other guy, die. And now it's going to go to be 0 when you plug in y equals 0. So we get a 0 plus, and then again, just like before, it's 2e to the 0 squared is 0 plus 0 squared is 0 plus 1, so 2e to the 1. So fyy, when we plug in 0, 0, is also 2e. And now we need to subtract fxy, plug in 0, 0. So what is that equal to? Man, I'm running out of colors. So we have fxy up here. We're plugging in 0, 0. But this x right here and this y right here, when you plug in 0, are just going to kill off the whole thing. We don't have anything added to the end of it. So that's just 0. So this is minus 0 squared, which is still 0. So what that means is that when we plug in 0, 0, this d function is 4e squared. 2e times 2e minus 0 squared. 4e squared. So that is our d of 0, 0. Okay, step 4, d of 0, 0. Okay, our last example here is going to be a word problem. Woohoo. So it says, Big John has determined that if he produces X thousand pounds of regular jerky a year and Y thousand pounds of teriyaki jerky a year, he'll make an annual profit in thousands of dollars, given by P of XY is that. Right? So there is our profit function. It takes in X thousand pounds of regular jerky, Y thousand pounds of teriyaki jerky, spits out in thousands of dollars, Big John's profit for the year. Now the question is, how many pounds of each type of jerky should Big John make in order to maximize profit? So if we're trying to find the maximum of the profit, and the profit is a function of two variables, that means we're trying to find the maximum of a function of two variables, and that points us towards using the d-test. Okay, so just like we have been, we're going to use the d-test. So go to your d-test, step 1, we need to find some partial derivatives. So px, notice we're taking the maximum, it's not called f anymore, it's called p, but it's okay, just use p instead of f, right? What I don't want to see is using f here, even though this function is p. I wouldn't count off, but it's just really annoying. So don't do that. So we want the partial of the profit function p with respect to x. So that's px. All right, anyway, what is that guy? Well, we get a minus 8x plus 6y minus 2. All right, py, what do we get? For py, we get 6x minus 6y plus 6. Okay, pxx, looks like we just get negative 8. And pyy, we get negative 6. And pxy, we get positive 6. Okay, so that's the end of step 1. Step 2, we need to set px and py equal to 0, so that's minus 8x plus 6y minus 2 equals 0, and 6x minus 6y plus 6 equals 0. Alright, so just like we did in the first couple of examples, we're going to solve this using substitution. You could also solve it using elimination. I'll show you both. So I want to show you 3 different ways. There are more than 3, but I'll show you these 3 ways to do step 2, however you want to do it, and then we'll move on. So first step is sort of like we've done before, where we solve for y using one of them. Whoops, I forgot to label this as py. I guess it doesn't really matter. That's okay. Okay, so the first time, let's do this one in, how about green? Okay, so what we'll do here is we'll use this equation and solve for y. That's the goal. So minus 8x plus 6y minus 2. Sorry, I didn't want to write that down. What I want to do is solve for y. So let's leave the 6y over here. I don't want the negative 8x. So let's make it a positive 8x on the right side. And then we're going to add 2. All right, so that's using this px equation. We solve for that 6y. And now we could divide by 6. And we'll get y is 8 over 6, which is 4/3 x, plus 2 over 6, which is 1/3. All right, so if you guys are thinking this way has fractions, I don't like fractions, I'm not going to do it this way, that's perfectly fine. You could stop here and say, no, backtrack, and I'll show you after this how you would do that. That's okay. You can go ahead and stop writing and just watch, and I want to show you that we'll get the same answer no matter how you do this. Okay, so if that's y, our goal would be to go back and plug that in for the y in the equation we didn't use. So we got 4/3 plus 1/3. That was y. Oops, 4/3 x, sorry, plus 1/3. So then in this equation, we would get 6x plus minus, not plus, minus 6 times 4/3 x plus 1/3 plus 6 equals 0. Alright, so notice we're multiplying by 6, and over here we divided by 6. So multiplying by 6, we're going to recover this 8x plus 2 when you distribute this 6 through. So that's 6x minus 6 times 4/3, we get 8x. And then it's a minus 6, so we're going to get a minus 6 times 1/3 is 2, plus 6 equals 0. And that gives us minus 2x plus 4 equals 0. Solve for x, and you get x is 2. So I'm going to write that up here. X equals 2. That was what we got using the green guy. Now solving for y, what do we get? Well, if y is 4/3 times x, that's 4/3 times 2 plus 1/3. 4/3 times 2 would be 8/3 plus 1/3 would be 9/3, and 9/3 is 3. So we get y equals 3. Okay, so that would be one way to do step 2. We took a piece of x, solved for y, plugged that back into piece of y in order to figure out what x was, and then went back into our equation for y in order to figure out what y was. So that's one way to do this. If you don't like the fractions and stuff, then I'll show you a different way that's very, very similar. I'm going to keep this x equals 2 and y minus 3 up here to just remember what we got so we can verify that we get the same thing every time. So if you were copying this down and you're not done yet, pause the video. I'm about to erase it. Okay, so now what if you didn't want to do it that way? What if you saw your fractions and you said, gross, get out of here, I don't want to do that. Okay, fine. I'll show you a different way to do it. And that's everything. Wow, okay, that took a while. Okay, this time we'll work in blue. So for my blue stuff, I'll put it up here. I'm going to get an x equals something and a y equals something. Hopefully it's still 2 and 3. So for blue, what I'm going to do is instead of solving for y up in the px, I'm going to solve for it over here in the py. So that guy's going to give me a y equals something. So what is that? Well, we've got a 6x minus 6y plus 6 equals 0. So let's add that 6y over, and we get 6x plus 6 is 6y. Now divide by 6, and you get x plus 1 equals y. Yay, this way didn't have any fractions. Hopefully you guys are happy about that. I mean, if you like fractions, great. I like fractions. They serve a lot of, good purposes. But I understand a lot of people hate them, and that's okay. Whatever. Okay, we got y equals x plus 1. So what we're going to do, just like before, is now take that y and plug it into the equation that we haven't used yet. When we do that, what do we get? We get minus 8x plus 6 times, and then instead of y, we get x plus 1 minus 2 equals 0. Okay, so that's now minus 8x plus 6x plus 6. Oops. Plus 6 minus 2 equals 0. That equation should look vaguely familiar. What we get out of that is minus 2x plus 4 equals 0. And what we get from that is x equals 2, just like we got when we did the stuff in green. So that's good. Now we go back to our y equals x plus 1, plug in 2, and you get 2 plus 1 is 3, so y is 3. Okay, that's exactly what we got before as well. All right, so there's another way, the blue way this time, of solving that system of equations, doing that second step. I'm going to show you one more way, which is something we haven't done yet. So if you are copying this down, pause the video. I'm about to erase. Okay, so this second way is something that you should have learned in Business Pre-Cal, and it's what I mentioned earlier, where instead of using substitution, which is the method we've been using to solve these systems of equations, what we're going to use now is called elimination. So let's go to purple. So this time in purple, I ought to get, again, x equals 2, y equals 3. We know that's the correct answer, but let's see if we can get to it a different way. So what we're going to do this time is take these two equations and add them. I'm going to add them because I've noticed that when I have, in this first equation, what I have is a plus 6y, and in this second equation, what I have is a minus 6y. So if I were to add these two equations, those would cancel. And what would I get? Well, I would get minus 8x plus 6y would be minus 2x plus 6y minus 6y. That's going to go away. And then over here I get minus 2 plus 6, which is plus 4. And then on the right side, 0 plus 0 is still 0. So adding the left side of my equation and the right side of my equation, those things are still equal. And hey, I get minus 2x plus 4, which should be familiar. Solving for that, you get x equals 2. So that was a little faster. But you have to recognize that for these, they're already positive 6y and minus 6y. If they aren't this exact same, you have to multiply the whole equation by something to make them the same before you can add those equations together and have something cancel. But anyway, so now when we get x equals 2, how do we figure out what y is? Well, what we have to do is just take one of these equations, how about the top one, and plug in x equals 2. So negative 8 times 2 plus 6y minus 2 equals 0. So that's minus 16, but then we'll have a minus 2 plus 6y equals 0. So that's minus 18 plus 6y equals 0. And now add your 18 over, you get 6y is 18, divide by the 6, and you get y is 3. And that's exactly what we got the first 2 times. Okay, so those are 3 different ways to do that second step. I don't care which one you do, as long as you do it correctly. They are all obviously get you the same answer, and that is the correct answer. So whichever way you liked most, run with it. Go for it. Okay, if you're still copying that down, go ahead and pause the video because I'm going to start erasing. Give myself some more room over here. Okay, so that's the end of step 3. What we ended up getting, no matter how you did it, is... First off, that was the end of step 2, not step 3. And what you got was the point 23 was our only critical value. Alright, so that was the end of step 2. I will say hopefully none of you think of this. You certainly do not have to do that 3 different ways. Just do it one of those ways. I was just trying to show you guys different ways to do it. I don't want anyone to think you need to do it more than one way. Hopefully no one is. Anyway, for step 3, we need to figure out what is the d of 2, 3. So for d of 2, 3, we go up to pxx, which was waiting back here from step 1. We're plugging in 2, 3, but it doesn't matter. That's always negative 8. Then we multiply by p of yy. We're plugging in 2, 3, but it doesn't matter because that's always negative 6. And then we subtract. We're plugging in 2, 3 to p of xy, but that's always 6. So that's minus 6 squared. Okay, so what is that? Well, negative 8 times negative 6 would be positive 48 instead of negative 48. And then minus 6 squared is 48 minus 36, and that's 12. Okay, so we got 12 from step 3. Now step 4, since d of 2, 3 was 12, and 12 is positive, that means we will have a maximum or minimum. Of course, from the very beginning, we were trying to find the maximum. So if we don't end up getting that this is a maximum, we certainly have made a mistake somewhere. But we have to do this check. You can't just say, I get 2, 3. I know that guy's going to be a maximum. You have to do the step 3 and 4 to check that it is a maximum. Okay, so to do that, we get that the d is of 2, 3 is 12, which is positive. We also need the second partial with respect to x of 2, 3. What was that? Well, that was negative 8, which is negative. So, yay, that does give us that 2, 3 is a maximum. 7.3, it's all about the d-test optimizing functions of 2 variables. If you guys have any questions over that, let me know or ask them in class.